All right, this is day 8 in our lesson about day 8 in our unit about exponents and exponential functions. And this is going to be a review lesson, so we're going to just sort of cover a lot of little topics that we've been working on. And let's just jump right in and start with remembering how to simplify exponential expressions. Remember that if you're going to have a negative exponent on a fraction, the way you handle that is you're going to eventually wind up doing the reciprocal and making this a positive exponent. But if I were you, I would first simplify what is inside the fraction here. So a to the 5th over a to the 7th power. Let's simplify that first. These 5 a's are going to cancel out 5 of these a's. So there won't be any a's left in the top, and in the bottom there will be 2 a's. So a to the 2nd power. Now we go ahead and do the reciprocal. So if I do the reciprocal and make this a positive exponent, instead of 1 over a squared, it'll just be a squared, because the reciprocal would be a squared over 1 if I turn this upside down, but we don't need the 1 anymore. So then that final answer is going to be a to the 4th power. Okay, and we're multiplying these. 2 times 2 is why it's 4. Okay, so that would be your answer to number 1. For number 2, in order to simplify this one, there's a couple of things. First of all, in the denominator here, we're going to multiply these. Whenever you have a power to a power, you multiply. So that's going to give me 7 to the 6th power. All right. For a minute, I'm going to leave this. You know what? I'm going to go ahead and do this. This is like having 7 to the 1 power. And when you multiply with like bases, you add the exponents. So this is going to be 7 to the negative 1 power right now. Notice you do not multiply 7 times 7 and get 49. Okay? If this were x to the negative 2 power times x to the 1 power, you would understand that it's just x to the negative 1 power, because I'm adding the negative 2 and the 1. This is x, this is x, this is x. Having this be a number doesn't change the way the pattern works. This is 7, this is 7, this is still 7, just like x stays x. It doesn't change to a y or something different. So you just add the exponents, that is all. Now it's time to do this. If you have a negative exponent on something, that tells you that the expression is on the wrong side of the fraction. So we can just take this and move it to the denominator. So that's going to drop down as 7 to the 1 power in the bottom. So that's gone now. So now there's nothing left in the top of the fraction. So I'm going to need a 1 up there. Putting these together, that's going to be 7 to the 7th power. So that would be your final answer for number 2. We're adding these. Okay, again, do not make any kind of a 49. That's the most common mistake I've seen. Now, okay, anything to the 0 power is 1. That doesn't mean x to the 1 power. It means basically it's like this is gone. Okay? Anything to the 0 power is 1. So I'm going to wipe that out and it becomes a 1, which we just don't need. Now, anything with a negative exponent is going to move. The numbers are not going to move. The negative 9 and the 15, they stay where they are. But the x to the negative 4 power, that's going to drop down. The y to the negative 4 power is going to go up. Okay, so that means what we have so far is this. We will reduce these. So both of these are divisible by 3, so I'll have negative 3 over 5. There I reduced those. Now your y to the negative 4 power comes up here and becomes y to the 4th power. The x goes down and becomes x to the 4th power. So that is going to be your final answer for number 3. Okay, looking at number 4, again, anything to the 0 power is 1, which is going to mean it's basically like getting rid of that. Okay, it's not there at all. I mean, it's a 1, but multiplying by 1 doesn't change anything. So with the -2, I actually have to do the 4th power, you know, so it's like having -2 to the 4th power. 2 to the 4th power is 16, you know, and -2 to the 4th power is still 16. Anytime you have an even power, you're going to wind up with a positive result because a negative times a negative is a positive. I will wind up multiplying here with the c to the 2nd power. So this will wind up being c to the 8th power. The same type of thing is going to happen on this one. Here I have to do 2 to the 3rd power. Okay, if you got rid of the variables, you see you have 2 to the 3rd power. That's 8. Alright, so notice I do not multiply, I do not get 6. But I will multiply with the exponent. So this will be b to the 6th power, and then just c to the 3rd power. And now we can move on to our final answer. I have to do 16 times 8. So that's going to be 128. And then putting these c's together, the 8 and the 3, so that's going to be c to the 11th power, and then of course I have b to the 6th power. So that'll be the final answer for number 4. Alright, taking a look at number 5. Basically, this is the situation where we add the exponents. So we can just add them all. 1 plus 3 is 4, and then 4 plus -2 is 2. So just adding up all those exponents, I have a squared. Okay, that's all there is to that. Now this one, we have the -6 and the 3. We're just going to multiply those. So that's going to be -18. And then x squared times x to the 3rd power, that's x to the 5th. We add those. And then y times y to the -2 power. You know, you can think of this as like y to the 1 power. So we're adding these exponents. So 1 plus -2 is -1. So that means that this is going to be dropped to the denominator. Okay, so this, because it's a negative exponent, has to drop to the bottom of the fraction. So I'm going to wind up having my y to the 1 power down here instead of up here. And then that's going to be my final answer. Okay, so I guess I'll recopy it. So the final answer is going to be -18 x to the 5th power over y. Okay? All right, number 7. All right, watch out. Once again, I have a negative power on a fraction. So eventually I'm going to wind up doing the reciprocal here. But let's go ahead and simplify what's going on the inside first. So what's going to happen? The y, this negative exponent, means this is going to have to go up. Okay, so I'm going to wind up with y to the 3rd power up in the top there. All right, because I'm going to wind up moving that. That's a little hard to see. Let me zoom in and do better. All right, let me try again. Maybe with a smaller pen. Okay, so this negative exponent means it's on the wrong side of the line. So this is going to have to go up and become y to the positive 3 power. Okay, so now that's gone. Okay, so let's go ahead and simplify everything. So right now I still have this -3 power. Now this 3 is not going anywhere. So that's going to still be here. And I have two x's in the top, one x in the bottom. This x is going to cancel out one of those x's, so I'll just have one x left in the top. Now that I moved that y up and made it positive, now I have four y's in the top. So this will be y to the fourth power. Alright, so now I have simplified everything inside the fraction. You should always do that first. Now, if you have a negative exponent on a fraction, you're going to do the reciprocal. So what I'm going to do is I'm going to take this fraction, and the 3 is going to wind up here. The y to the fourth power is going to wind up down here. And now I'm going to make this a positive 3 power. Then I can go ahead and do the exponent to everything. So this is going to be 9, all right, 3 to the third power, over x to the third power, and then y to the 12th power. So that would be your final answer for number 7. All right, moving on to number 8. The fact, we have this multiplication, these two fractions, you can just view this as one big fraction. Okay, so if I were you, the first thing I would do is sort of collect everything into one fraction anyway. So, we've got our negative 20 and our 5. But, okay, x's. We have x and x squared. Together, that makes x to the third power. The y's. We have y to the fourth power and y squared. Together, that makes y to the sixth power. You can think of it as addition if you want to. In the denominator, we have x to the third power, x to the third power. That's x to the sixth power. And here we have 2 y's and an extra y, so that'll be 3 y's. So collect it all together first. Now we can go ahead and simplify everything. Reducing the 20 over 5, of course 5 goes into 20 4 times. So that'll be negative 4 up there. 3 x's in the top, 6 in the bottom. These 3 x's will cancel out 3 of these x's, and that's going to leave 3 x's in the bottom. Similarly with the y's. These 3 y's are going to cancel out 3 of these y's. So that's going to leave 3 y's in the top. So that's it. This is going to be your answer. Okay, so that's number 8. Alright, number 9. This is one of those real world problems where we are using either exponential growth or exponential decay models. So let's see. You invest $3,000 in an account that earns 4.5% interest, compounded quarterly. What? Okay, you know what? In class we did not talk about compounding quarterly, so let's just change that to annually. Let's just change that to annually. That's another lesson talking about compound interest, and we're not doing this right now. So let's just change that to annually. Okay, so the way we model this, this kind of exponential growth is that, remember, we do that initial amount times 1 plus the rate to the power of time. That's the setup of this. So right here we put the initial amount. So kind of starting over, that initial amount is $3,000. Okay, and then we're supposed to do 1 plus the rate. Well, the rate is going to come from this percent. And here we see that's 4.5%. So that translates into 0.045. Okay, so that's the R value. So we're doing 1 plus 0.045 to the power of time. Of course, we're not going to leave it as 1 plus 0.045. We're going to go ahead and put that together and just say 1.045. okay, to the power of time. So this is the model that we're using. Since it's 10 years, then we will just let t be 10. Okay, that will give us the balance in 10 years. So you could just type this into your calculator. Okay, so what was it? 3,000. So 3,000 times 1.045 to the 10th power. So in 10 years, we would have $4,658.91. Okay, so that is how you would do number 9 if we go ahead and change this to annually, which I want you to do. Okay, for number 10, same type of thing. The population is growing at a rate of 1.5%. Predict the population in 1996. Okay, so we start with that initial amount of 1,215,112, and now we're going to do 1 plus the rate. Okay, this 1.5% translates into an R value of 0.015. So I'm going to do 1 plus 0.015, which of course is 1.015. All right, so I'm going to go ahead and put those together. All right, so that's the model that we're using. Predict the population in 1996. Look, if we are starting in the year 1990, all right, that's where we got this initial value from. And then we're ending up in 1996. That means t, the time is 6 years have gone by. So we will put this in our calculator, but we will let t be 6. So if you do that, so here I've typed it in, and this would be my new population 6 years from now. Okay, so 1,328,656. All right, moving on to number 11. Because there's no number here added onto the end, I know that the asymptote is going to be the x-axis. This is the line where the function will get closer and closer to it, but not reach it. So there's that. So after that, I'm just going to put this in the calculator. So 3 to the x plus 2 power. All right. In the TI-30, we can just hit the table button. Let's clear this out. So this was 3 to the, all right, what did it say? Yes, 3 to the x plus 2 power. And I'm just going to hit enter a few times. Whoa, didn't mean to do that. Okay, I'm just going to let it start at 0. And let me put this back to auto for now. All right, let's see what we have. Now, my idea is to look for the numbers that fit. So here, looking at the bottom of my calculator, I see 81, 27. These numbers are too big. So coming from the bottom of the calculator, the first numbers that will fit are 0 and 9, and then it goes from there. So I'm going to really start at the bottom of my chart and use my 0, and then it's going to go from there, like -1, -2, -3, -4, because this is the first number that fits. Okay, so 0, 9, -1, 3, So I've got 3 and 1. Okay, and then as it goes up from there, I've got 1/3 and 1/9. I feel like toggling that. I know what 1/3 is. Okay, so that's like 0.1. All right, so 1/3 is about 0.3, and this is about 0.1. So these are the 5 values that we should use. Okay, so now we can graph this thing. So at -4, we are looking at 0.1. So at -4, we are almost pretty much on the line. All right, it's pretty close to 0. -3, not too much different, it's a little bit up. And then at -2, we're up to 1. And then at -1, we're up to 3. And then at 0, we are up to 9. Okay, so your curve should look very much like this. Notice on this end of the graph, I appear to be tracing the axis. All right, and that's the way it looks because ink has thickness. But in your mind, you should understand that the graph does not really touch the asymptote. It never really gets there, even though it looks like it. So your curve should look something like this. All right, please make sure your curve goes all the way to the edge of your graph. So I know that you know it doesn't go below the line. Now the domain is going to be -infinity to +infinity because it goes left forever and it goes to the right forever. The range, it does not go to -infinity. It starts here at 0. So the range will be 0 to infinity, all right, because it starts from here and goes up. By leaving this as a parentheses, we are not including 0 itself because the graph doesn't actually get to the asymptote. The asymptote is the line y equals 0. Don't just put 0, you have to put y equals 0. The y-intercept. The y-intercept is always going to be 0 comma something, obviously, because it's on the axis, and there it is. So the y-intercept is 0 comma 9. Now, the transformations, there's only one transformation from the parent function. All right, the parent function was 3 to the x power. So this little +2 here is the only change. And that +2, in the exponent, those are left-right changes. And they happen the opposite of the way they look. So that +2 is actually a translation left 2. Okay? If this were -2, it would be to the right. Remember that if I had numbers added onto the end, like if I had a, if I had a +5 out here or something, that would be up 5. But there's none of that on this particular problem. So we're done with number 11. Okay, let's take a look at number 12. Does that say number 11 twice? That's 11. And then this also says 11. Okay, let's look at another number 11. That's silly. Just type this equation into the calculator. 2 times 1/3 to the x minus 1 power. Of course, hit your table button. Yeah, okay, so 2 times 1/3 to the x minus 1 power. So x minus 1, and then what was that? -5. So -5. Just type it in your calculator. I'm just going to start from 0 for right now. Now, as far as knowing which values to use, look for the big values. Big, big, big. 481, that's a huge value. That is not going to fit on the graph. So from there, I will look for the first value that will fit. 13 is pretty close. How big is this graph? 13 won't quite fit. I'm going to go down one more. Whoa, from there it goes all the way to 1. No. Okay, you know what? I might try to squeeze in 13, even though it's a little bit off the graph. If you started with 0 and 1, that's fine. That's fine as well. But I'm going to start with -1 and 13. Okay, so I've got -1, which is 13. So then I will have 0, 1, 2, 3. I'll go ahead and put 4 in case somebody started with 0, since 13 doesn't technically fit. So at the 0, we've got 1, 3, and, well, 1, -3. And then we've got, let's look at the decimal, -4.3. And then the next one is -4.7. And then the last one is -4.9. Now, based on this value right here, we know that the asymptote is y equals -5. So let's go ahead and graph that. So this is the asymptote right here at y equals -5. Show the asymptote as a dotted line. And then graph your points. Alright, -1 is 13, so this is like 11, 12, 13. It would be like up here. 0, 1. 1 is -3. 2 is -4.3. 3 is -4.7. And then 4 is -4.9, which is pretty much, it's going to appear to be on the line. So when you graph it, I'm going to be connecting these dots, but start from the edge of the graph. On the right hand side, it's going to appear to trace the line. But we know that it doesn't actually touch. Okay, so your curve should look very much like this. So the domain is -infinity to +infinity. The range goes from the asymptote up, so the range will be from -5 to infinity. The asymptote we knew right away was going to be y equals -5. The y-intercept is always 0, something. In this case, it's 0, 1. Transformations. Compared to the parent function of just 2 times 1/3 to the x power, this has 2 transformations. This -5 on the end is going to drop us down 5. So that's one transformation. This -1 in the exponent is going to move us to the right 1. So this on the end works just like you would think. A negative makes you go down, a positive makes you go up. In the exponent, this is left-right motion, but it works the opposite of what you would normally think. So a negative number will actually send you to the right. If this were a positive one, then it would be to the left one. It's kind of backwards. All right, let's move on to number 12. Let's put this in the calculator. Here is the equation in the calculator. I used the table function, just typed it in. And I hope I used the right kind of negative sign. Okay, again, I'm going to look for the giant numbers that don't fit. It looks like the big numbers are here at the bottom this time. So here at the bottom, I'm seeing negative 200 and stuff. So these are the big numbers. I mean, technically, they're very small numbers, but you know what I mean. They're large values if you look at the absolute value of them. They won't fit on the graph. They're too low. 13 will not quite fit, but it's close. I might use it anyway. Negative 5, negative 1, 1, 2, 5 over 2. Okay, I'm getting some good values here, so I'm going to go ahead and start with the negative 5. That's the first value that will truly fit. And I scanned ahead and I see a bunch of nice values that will be very useful. So at the bottom of my chart, I'm going to put 3 and negative 5. So here we go. We have 3, negative 5. And then I'm going to go from there. Then it will be 2 and 1 and 0 and negative 1. Okay, so that's going to be 2. So it's going to go negative 1, negative 1, positive 1, 2. Alright, and that last value is 5 over 2, and that is 2.5. Okay, so these are good values to use. Now, I know that the asymptote, because of this number, is going to be y equals 3. So you can go ahead and put your asymptote as a dotted line like we always do. Okay, now I will graph these values. Negative 1 is 2.5. 0 is at 2, 1 comma 1. 2 is at negative 1, and 3 comma negative 5. So these are the values. So you can see how the curve is going. Of course, it's going to swerve and approach the asymptote. By the time it gets to the end, it's going to appear to trace this asymptote. Okay, and until it curves to hit these values. Okay, so your curve should look something like this. Make sure your graph extends all the way to the ends of the graph. Now the domain is always going to be negative infinity to positive infinity. Left forever, right forever. The range, however, you have to give the range from bottom to top. And this graph goes from negative infinity, down here at the bottom, up to a height of 3. Alright, it's always going to be that asymptote. So it has to be in this order. Negative infinity to 3. 3 is like the ceiling. We knew the asymptote was y equals 3. Do not just put 3, it has to be y equals 3. The y-intercept is always 0 comma something. In this case, it is 0 comma 2. Alright. I forgot to ask you about the transformations. Let's go ahead and say them anyway. Let's just write them in. Transformations. Alright, there are 2 transformations. The plus 3 on the end is going to send us up 3. And then the negative in the front is a reflection over the x-axis. Alright, so those are the 2 transformations. Alright, now we just got to solve these little equations. Solving this first equation is going to be really simple. If the bases are the same, then the exponents are the same. So we can go ahead and set these equal to each other like so. All we have to do now is let's subtract 2x from both sides. That's going to give me negative x is equal to negative 3, which means that x will equal 3. Technically, you could say I divided both sides by negative 1 just now. Now, number 14. We need these bases to be the same to be able to do the problem. there's no way for me to write 27 as 9 to a power. So I need to change both of these bases to a 3. Fortunately, 9 can be written as 3 squared, and meanwhile 27 can be written as 3 to the third power. So that way they're both base 3. I have to be careful, what do I do with the existing exponents? And the answer is I just put them in parentheses. So I'll have my 2x right here, and I'll have my x minus 1 right there. Now, I'm going to wind up multiplying those together. So this is going to wind up as 3 to the 4x power, 2 times 2. And this is going to wind up as 3 to the 3x minus 3 power. Had to do the distributive property. Now that the bases are the same, the exponents will be the same. So I can go ahead and set the exponents equal to each other now. Subtracting 3x from both sides, sorry, so those are gone. That gives me x equals negative 3. So that is the answer for number 14. All right, similarly, on number 15, we need these bases to be the same. I can tell that 4 can be written as 2 squared. So I can go ahead and keep this one, okay, 2 to the 3x. But this 4 has to be written as 2 squared. Okay? I've still got this x minus 1, just put it in parentheses. So that means I'll have 2 to the 3x power equals 2 to the 2x minus 2 power. Again, with the distributive property. Now that the bases are the same, the exponents must be the same. If I subtract 2x from both sides, that's going to give me x equals negative 2. So that's number 15. 16 is the trickiest one, so we'll just have to be very, very careful. The key is knowing what to do with this 125. 125 cannot be written as 25 and a power. So I'm going to have to change both of these bases. I know that 25 can be written as 5 squared. You know what? I'm going to make this a little bigger. Okay, 5 squared. And then I still have the 10x plus 8 sitting there. So it's just a matter of what do I do with this 1 over 125? Well, let me just remind you of that real quick. 1 over 125. Okay, focusing on the 125. This is one of the ones I had wanted you to memorize. 125 is 5 to the third power. So if you haven't memorized that, you need to memorize that 125 is 5 to the third power. So to write this as just a base and a power, this is really 5 to the negative 3 power because it's in the denominator. All right, so that means I can take this 1 over 125 and replace it with 5 to the negative 3 power. Again, this existing exponent, I just put it in parentheses, negative 2x plus 4. So that's going to give me 5 to the 20x plus 16 power is equal to 5 to the 6x minus 12 power. In both cases, I did the distributive property. Now that the bases are finally the same, I can set the exponents equal to each other. So that means that 20x plus 16 will equal 6x minus 12. I would subtract 6x from both sides, so that's going to give me 14x plus 16 is equal to negative 12. Then I will subtract 16 from both sides. So that's going to give me 14x is equal to negative 28. Last step is to divide both sides by 14. Okay, and that is going to give me x equals -2. Can I squeeze this in? Maybe I'll have to put it over here. X equals -2. And that is how you do that. All right, this video has been pretty long, but I hope I was able to answer all your questions. So this was a nice little review of dealing with exponents. We solved some equations, we graphed, we did some real-world problems, and we practiced our simplifying exponential expressions. So I hope this has been helpful to you. If so, a like, a thumbs up is always appreciated. And either way, I look forward to seeing you on the next video.